So hi students, in this video I am going to explain the topic center of mass. This is the second video in the series for the chapter System of Particles and Rotational Motion, that is NCERT volume 1 for class 11. Now as in the previous video we have discussed the basic concept of rigid body. In the concept of rigid body, we have not ignored the finite size of the object. In the chapter rotational motion, this size of the object is not neglected, but in laws of motion and other chapters, work energy, power, motion in 1 dimension, 2 dimension, we have assumed the moving object as point object. Now for objects which have finite sizes, the motion of such objects is discussed with reference to a particular point, and that particular point is called center of mass. Now center of mass is, the two things are very important with reference to the concept of center of mass. First thing is, the entire mass is supposed to be concentrated at the center of mass, and all the external forces were assumed to be acting at center of mass. Now how to locate the center of mass for a n particle system? Now for n particle system, suppose this is a Cartesian coordinate system. So this is x-axis, this is y-axis, and this is z-axis. Okay. Now suppose n particle system means, suppose you have a rigid body, and this rigid body is composed of n particles. This is particle of mass m1, this is particle of mass m2, and suppose this is particle of mass mn. Suppose this m1 is defined by position vector r1, m2 is defined by position vector r2, and mn is defined by position vector rn. Then position vector of the center of mass, it is given by m1 r1 plus m2 r2 and so on, mn rn divided by m1 plus m2 plus and so on mn. So this can be written as, our center of mass of the position coordinate can be written as summation I is equal to 1 to n mi ri divided by summation mi. So this is the general expression for center of mass, locating the center of mass of a n particle system. Okay, now two things to be observed. First thing is, the position of center of mass COM, center of mass, is independent of coordinate system. Even if I change the coordinate system, the position of center of mass will remain same. The position of center of mass is independent of coordinate system. Okay, and the other important thing is, the position of center of mass depends on the shape of the body and distribution of mass. The position of center of mass depends on shape of body and distribution of mass. So you must note down these 2 points. Okay, so this is the basic concept. Suppose this is for n particle system, this is how you have to locate the center of mass. Now this n particle system, the distribution of mass can be discrete or it may be continuous. Okay, so if the mass is continuous, then I can break this down expression into RCM. See, RCM can be broken into XCM I cap plus YCM J cap plus Z, or you can call it ZCM K cap. Okay, so where XCM, YCM, ZCM are the X, Y and Z coordinate of the center of mass, such that XCM will be M1 X1 plus M2 X2 and so on, Mn Xn divided by M1 plus M2 plus Mn. Okay. Similarly, you can write the expression for YCM and ZCM. Okay. Now, if this, in case the mass distribution is continuous, then this thing can be written in calculus form as integration x dm divided by integration of dm. Okay. So integration of x dm divided by integration of dm. Now let's see how do we use this expression to locate center of mass. Now suppose we have to calculate the center of mass of a rigid rod whose mass is m and length is l, and it is a uniform rigid rod. Okay. Now suppose this is the uniform rigid rod, and suppose it is placed along x-axis. So let's say this is x-axis and this is y-axis. So this is a rod of mass m, length l placed along x-axis. So obviously the center of mass will lie on the rod, and rod is along x-axis. So that means the y coordinate of center of mass is 0. It must be 0. Now our goal is to calculate the x coordinate of the center of mass. So let's see how we will do it. Now take one small element of length dx. It is at a distance x from the origin. This is the origin. Okay. Now let's say this dx element has a mass dm. Okay. So we wrote xcm as integration x dm divided by integration dm. So this is dm and its distance from origin is x. Okay. Now this is integration. That means you have such elements, small elements from this end to this end. Now suppose this differential element is located at this point. So its distance from the origin will be 0. So x will be 0. So you can have such small elements from this end to this end. So at this end, extreme end, the value of x will be L. So that means the value of x varies from 0 to L. 0 to L. So this is also 0 to L. Okay. Now as you can see, the general expression, the denominator has total mass. This is 0 to L dm. Okay. Let's see whether we are getting the total mass of the rod from this expression or not. The total mass is m. Now for this length dx, see, this is the elemental length dx. The total length of the rod is L. Now mass per unit length is m by L. This is mass per unit length. So if I multiply this quantity with dx, that is dm. Dm is the mass of this element. M by L is the mass per unit length. So mass per unit length into length of the small element is equal to mass of the small element. So instead of dm, I can write this expression. So 0 to L dm is equal to 0 to L m by L dx. So if you integrate dx, you get from between the limit 0 to L, you get L. So L cancels out and you have m. Okay. So this way you can check whether your proceeding is correct or not. So if I substitute this value 0 to L x dm is m by L dx Denominator you have 0 to L dm. So you have m by L dx, x dx. If you integrate x dx, you have m by L, L square by 2, and this is m, this is already m. So this m cancels out, L, so this is L by 2. So xcm is equal to L by 2. So that means the position of or coordinates of center of mass, ycm is already 0. So coordinate of center of mass will be L by 2 comma 0. See, even a common sense tells that for a rod of length L, the center of mass will be at the midpoint. And using this concept of center of mass also, we have obtained it as L by 2 comma 0. Okay, so next we will see how to calculate the center of mass of a semicircular ring. Okay, this is the center of mass of a rigid uniform rod. Okay, so next we will calculate the center of mass of a semicircular ring. So suppose this is a semicircular ring, and this is the y-axis, this is the x-axis. So ring is at this particular, ring is between this level, this is the ring. So ring x-axis, this is y-axis. The ring is of mass m and radius r. Now let's say this is one small element which is subtending and small angle d theta at the center, radius is r, this is theta. So if this is r, this radius is r, this angle is theta, so this is a small element. So the small element will have, if this is r cos theta, this is r sin theta, this is r cos theta, this is r sin theta. So that means this element will have x coordinate r cos theta and y coordinate r sin theta. Okay, so now we know the x coordinate and y coordinate of this differential element. Now x coordinate of the center of mass is integral x dm divided by integral dm. Okay, now this, see, this differential element can lie from this point till this point. Now if this element is at the location of this differential element is at this location, then the value of theta will be 0. This lies at this particular position, and if this element lies at this position, the value of theta is pi. So that means the value of theta goes from 0 to pi. So this thing can be written as x coordinate is r cos theta, so r cos theta, limit 0 to pi. Now what is dm? Dm is the mass of this element. Now what is the mass per unit? Suppose this element is, what is the length of this element? This radius is r, this is theta, so this arc length, so this will be r d theta. So r d theta is the length of this element. Okay, now total mass is m, total length, radius is r, so total length is pi r, circumference is twice pi r, so this half length will be pi r. Okay, so that means dm is the mass of this small element. Mass per unit length is m by pi r, and the length of this small element is r d theta. So I can write dm is equal to m by pi r into r d theta, mass per unit length into length of the segment. So this is m by pi r into r d theta, 0 to pi, m by pi r d theta. Now in the general expression for the center of mass, we know that the denominator must represent the total mass. Now this r and r cancels out. D theta, if you integrate d theta between 0 to pi, you get pi, so that pi and this pi cancels out. So you have only m, that is the total mass. So the expression for dm is correct. So this is how you can check that whether in the expression of dm the substitution is proper or not. If you integrate this denominator, you must get the total mass. Okay, now so this is total mass m. This m and this m cancels out, this r and this r cancels out, so you are left with r by pi HCm is equal to r by pi 0 to pi cos theta d theta. Now 0 to pi cos theta d theta is how much? R by pi cos theta is sin theta, so this is sin pi minus sin 0, so that is equal to 0. So that means HCm is equal to 0, that is x coordinate of the center of mass is 0. So this is x coordinate, we obtained the x coordinate. So next our target is to get the y coordinate of center of mass. So YCm, by the same logic, YCm will be 0 to pi r sin theta m by pi r d theta divided by 0 to pi m by pi r d theta. How did I write this? YCm is integral y dm divided by integral dm. So what is y? Y coordinate of the small element. Y coordinate of the small element is RCm. dm is already, we have got dm, this quantity. So we have this result. Now if we integrate this, again we get m. This m and this m cancels out. This r and this r cancels out. So we are left with YCm. YCm is equal to r by pi integral 0 to pi sin theta d theta. Okay. So this is r by pi, integration of sin theta is minus cos theta, 0 to pi. Okay. So this is r by pi, let's say take minus sign outside, so this is cos pi minus cos 0. Cos pi is minus 1, cos 0 is 1, so minus 1 minus 1 minus 2, this is minus, so this is twice r by pi. That means we have y coordinate of the center of mass as twice r by pi. So now we have got the x coordinate and y coordinate of center of mass. X coordinate is 0 and y coordinate is twice r by pi. So we can write the final result as the coordinate of the center of mass for a half ring or a semicircular uniform ring as, oh, let me write the result here. So for this semicircular ring, uniform ring of mass m and radius r, if it is placed like this such that the center of the ring, half ring, coincides with the origin of the xy coordinate system, then the coordinate of the center of mass will be 0, twice r by pi. This is the coordinate of the center of mass. So center of mass will lie along y-axis at distance twice r by pi from the origin. So this is the derivation for center of mass of a semicircular uniform ring. So let's solve one question based on the concept of center of mass. This is a simple question from Concept of Physics, chapter 9, question number 4. The question says, if you have a uniform disk of radius r and is put over another uniform disk of radius twice r of same thickness and density. Now how the two disks are placed? The peripheries of the two disks touch each other. That is the edges, they touch each other, and we have, the goal is to locate the center of mass. Okay, now let's see how we will proceed this question. First, let us draw the diagram. So this is the bigger disk of radius twice r, and this is the smaller disk of radius r. Okay, this is the origin, this is x-axis, this is y-axis. Okay, so this is the bigger disk. Now let us name the bigger disk as number 1 and the smaller disk as number 2. Okay, now both the disks have same thickness and same density. Okay, so mass of first disk m1, mass is volume into density, volume is area into thickness. So area is m1 is the mass of the bigger disk. Bigger disk, see, so this bigger disk has radius twice r, this is twice r. So from this point to this point it is r, from this point to this point it is r. So that means, see, for the smaller disk the radius is r, for bigger disk the radius is twice r. So coordinate of this is 0, 0 and this point will be r, 0. Okay, so now 0, 0 is the center of mass of the bigger disk and r, 0 is the location of center of mass of the smaller disk. Now position of center of mass, it is xcm, it is m1 x1 plus m2 x2 divided by m1 plus m2. Now I know the value of x1 and x2. This is x1, this is x2, but I don't know the value of m1 and m2. Now let's say how we can write the value of m1. Now m1 is pi, 1 is, remember, 1 is the bigger disk, 2 is the smaller disk. So pi into twice r, pi into twice r square. This is area into thickness t into density rho. So this is the mass of the bigger disk. M2 is pi r square t rho. This is the mass of the smaller disk. So if I substitute these values over here, xcm will be, for smaller disk, m1 pi twice r square t rho. What is x1? It is 0. It is 0 plus m2 pi r square t rho into x2. x2 is r divided by m1 plus m2, that is pi twice r square t rho plus pi r square t rho. Okay, so this is xcm. So this quantity is 0. So xcm is equal to t rho all cancels out, pi also cancels out. So what are we left with? This is pi r cube t rho, pi r cube t rho. Here you have 4r square, this is r square, so 5 pi r square t rho. Okay, so pi gone, t rho gone, this r cube r, so this we are left with r by 5. Now ycm, y coordinate, here it is 0, here also it is 0, so obviously ycm will be 0. So this implies the coordinate of the center of mass for this system, it will be r by 5, 0. Okay, so this is the final result. For this system, the center of mass will be located at r by 5, 0. Now see, our common sense should also hint you or point you towards the answer if this question was asked in objective type question, because this is a disk. Suppose only you have this disk, the center of mass will be at this particular location. Now when this smaller disk is placed on over this larger disk on this side, towards right hand side, towards this side, so this part will be heavier, this part this part will be heavier. So center of mass will always shift towards the heavier side. So that is why we are having r by 5 comma 0. Center of mass will shift in this direction and it will be at x equal to r by 5. Okay, so this is the final result. So this was a brief discussion on the topic center of mass. I hope it was of some benefit to all the students, and the next preceding videos I am going to discuss the motion of center of mass, followed by discussion of concept of torque and angular momentum. And thank you for watching this video.